Hello everyone, in this mathematics and calculus tutorial we explain how to solve double integrals using polar coordinates. Here is the problem that we want to solve. We want to calculate the value of this double integral where the domain of integration d is the circle with a radius of 1. When solving problems of this type, the first step is to sketch the integration domain and to represent the integration domain in the polar coordinates. But before we do that, let us answer the following question. Why it's suitable over here to use polar coordinates instead of using Cartesian or rectangular coordinates? Well, this is because of two reasons. First of all, we can see that the domain of integration is circle. And it's more natural and mathematically easier to describe a circle or circular region in polar coordinates than it is in rectangular coordinates. This was the first reason. And the second reason is because of this function that we want to integrate. If you carefully look at this function looks like a circle. Namely, if you put 1 minus x squared minus y squared to be equal to 0, that is, if you put this thing to be equal to 0, and if you transform this equation, you will see that this is an equation of a circle. And with a suitable change of coordinates, that is, by using polar coordinates, we will be able to significantly simplify this function. You will see this later on in this video tutorial. Okay, the first step is to sketch the integration region. Here, I will sketch x and y plane. This is x-axis and this is y-axis. And over here is our circle. The radius of the circle is 1. And I'll do my best to sketch a circle over here. Okay, then like this. And then probably I need to go a little bit further over here. Not bad. Doesn't look bad, right? Here it's 1, 1, minus 1, and minus 1. First of all, let's describe this region by using Cartesian coordinates. This region over here, D, is a set, and it's a set of points whose coordinates are x and y. That is, any point over here has two coordinates, has x and y. Okay, now, these x and y should satisfy the property that they're inside of the circle. This circle has a radius of 1, and if you remember the canonical form of an equation of the circle, you will remember that the equation of a circle looks like this. This is a circle centered at the origin with a radius of r. In our case, the radius is obviously 1, so the equation of a circle looks like this. However, this equation means that we are actually taking the points on the actual circle, and we are not taking the points inside of a circle. Inside of a circle is actually described by this equation. Consequently, to take all the points inside of the circle and on the boundary of a circle, on the edge of the circle, our equation should look like this. And over here we will simply write it down. So these sets of points and their coordinates have to satisfy this equation. And this is our region D. Next, let's introduce polar coordinates and let's express this set in polar coordinates. Over here I will sketch again a coordinate system and the point over here. This point has coordinates x, y, and this distance over here is x, and the distance over here is y. This is 90-degree angle, and this is also 90-degree angle. Now, what I will do now, I'm going to draw a vector from the origin to this point. And here's the vector. The length of this vector is r, and the angle that this vector is making with the x-axis is denoted by theta or theta, however you like to pronounce this Greek symbol. R and theta are our polar coordinates. Now, by using simple geometry, we can transform x and y coordinates into r and theta and vice versa. So let's derive the equations. So what do we have? We obviously have that x is r cosine theta and y is r sine theta. Good. Consequently, if we know r and theta or theta, we can compute x and y. Now, let's use these two relations and let's try to simplify this set, or better to say mathematical description of this set. We can write x squared plus y squared is equal to, instead of x, we will write this expression squared, r squared cosine squared theta plus r squared sine squared theta, and obviously this is equal to r squared, and in parentheses we have cosine squared theta plus sine squared theta. And since cosine square alpha plus sine square alpha is equal to 1 in the general case, we also have that cosine square theta plus sine square theta is equal to 1. Consequently, this expression becomes 1, and over here we have that this is equal to r squared. So what is now the consequence? The consequence is that this equation over here can be written in the polar coordinates simply as r squared is less than or equal to 1, and since r is always positive, this equation over here becomes r is less than or equal to 1. And that's it. That's the simplification. Consequently, our integration domain set D can be expressed mathematically like this. It's a set of points with polar coordinates r and theta, where r is less than or equal to 1, but what should theta satisfy? What is the relation that theta should satisfy? Let's see over here. If we fix the value of r, for example, this value over here, theta obviously varies from 0 to 2 pi. That is, for any fixed value of r, theta will go from 0 to 2 pi. Only like that we can describe the complete circle. Consequently, theta is in the interval given over here, 2 pi, and that's it. Note over here that you have to express the angles in radians. It would be a mistake and you will not arrive at the correct conclusion and the correct result if you use degrees over here. This is very important to keep in mind. Let us now briefly summarize what we achieved so far. Here is our original integral. Then we introduced polar coordinates and these two equations. And by using these two equations, we were able to significantly simplify the mathematical description of our integration domain. Now, everything looks good here. That is, we can substitute x by this value, y by this value, and the integration domain is given over here in polar coordinates. However, the issue is how to approximate dA over here. In the sequel, I will teach you one elegant method for approximating dA. And here's the main idea. First of all, we are going to construct a line that creates an angle of theta with respect to horizontal line. So here's a horizontal line and here's an origin. And over here is a line, or better to say, a direction that makes an angle of theta with respect to the horizontal axis. Next, over here, I'm going to increase this angle theta for an infinitesimal small value of d theta. And over here, I'm going to obtain a new line, and here it is. This angle over here is d theta, and I'm going to denote it over here. Note over here that d theta is an infinitesimally small angle, and everything that you can see over here is exaggerated. That is, in reality, this line is almost the same as the original line, and you will not see any difference. However, for illustration purposes, I need to make this graph to be more exaggerated. Then, over here, let us construct a vector whose length is r, and here it is. The length of this vector is r. Now, as this line rotates, this vector over here will describe an arc or a segment of a circle, or better to say, its top will describe an arc. And as we rotate the line for the small angle of d theta, the vector will go to this position. And here it is. And this is now also r. Next, let's increase the length of our vector for dr, where dr, again, is an infinitesimally small value. That is, this distance over here is dr. Now, we can imagine that there is another vector over here, that is the vector whose length is r plus dr, and as this vector rotates, its tip, or the top of the arrow, will also describe an arc. And after rotation, the vector will go over here, and this will be the position. Okay, now let's isolate this segment over here, constructed by rotating the vectors. Here it is. And over here, I'm going to write it again, or draw it again, just for illustration purposes. And I'm going to a little bit exaggerate its dimensions such that you can see everything nicely. So here's our segment. Let me try to sketch it. Here it is. The length of this side, or the length of this edge, is dr, as well as this one. Now, since this angle d theta is in radians and this distance is r, the length of this arc over here is actually r multiplying d theta. How about the length of this arc over here? Well, the length of the vector that describes this arc is r plus dr. So we will write r plus dr, and the described angle is the angle of d theta. Consequently, this distance is r plus dr multiplying d theta. Now, we will introduce one very important and justified assumption. dr is very small. It's an infinitesimally small value. And again, everything drawn over here is an exaggerated situation. Since dr is very small, the length of this arc is approximately equal to the length of this arc. That is, we can write r plus dr multiplying d theta is approximately equal to r d theta. This was our first approximation. The second approximation is that we can approximate arcs by straight lines, since this angle d theta is in an infinitesimally small angle. Consequently, this whole segment can be approximated as a rectangle. And let's sketch the rectangle over here. Here it is, where the length of this side or this edge is r multiplying d theta, and after this approximation the length of the top side is also r d theta, then the height is dr. Now, dA is actually the area of this segment. Consequently, we can write dA is equal to r multiplying d theta multiplying dr, and that's it. This is the expression for dA that we will use in this integral. Here is our last equation for evaluating this integral. dA is r multiplying dr multiplying d theta. And now we are ready to solve our integral. So let's write it down. Our integral I becomes, here is our first integral, here is the second integral. Over here, we have integration with respect to r and theta. So let's choose the order of integration. This is another very important step that you have to perform very carefully. First, we will integrate with respect to r, and consequently let's write the bounds for r. The bounds for r are from 0 to 1, and the bounds for theta or theta are from 0 to 2 pi. Okay, so let's see what we are left with inside of this inner integral after we substitute the values. So let's substitute the value over here. We have 1 minus x squared minus y squared is equal to, let's write it down, 1 minus, instead of x, we write this expression, r squared cosine squared theta minus, instead of y, we will write r squared sine squared theta. Let's just nicely write things here. So we are left with 1 minus r squared cosine squared theta plus sine squared theta. And as the result, we are left with 1 minus r squared multiplying 1. This is because cosine squared theta plus sine squared theta is 1. That is, we are left with 1 minus r squared. And let's substitute this value. We have 1 minus r squared, and instead of dA, we have r multiplying dr d theta. Good. Let's evaluate this integral over here. We have first integration 0 to 2 pi. Then let's simplify this expression over here. We will have 0 to 1. Then inside we will have r minus r to the power 3 dr. I will use parentheses to denote the order of integration, and then after that we will have d theta. So the idea over here is to integrate with respect to r and then to integrate with respect to theta. So let's integrate this expression with respect to r. As the result, we obtain this. We have an integral from 0 to 2 pi. Inside we have r squared divided by 2 minus r to the power 4 divided by 4, where we also have the bounds. The bounds are from 0 to 1, and we are only left with d theta. Next, we need to substitute the bounds. We are left with integral I is an integral from 0 to 2 pi, and over here we have, if we substitute the bounds, we have 1 over 2 minus 1 over 4 and over here we have d theta. Next we have an integral from 0 to 2 pi, and over here we have 1/2 minus 1/4 is actually 1/4, or 1 divided by 4, and this 1 divided by 4 can go outside of the integral and we are left with d theta. And now an integral of d theta is simply theta, and we have the bounds from 0 to 2 pi, and if you substitute the bounds we will have 1/4 multiplying 2 pi, and this is obviously equal to, let's see, pi over 2. And this is the final value of our integral. Okay, that's all for today, and thanks for watching.